Welcome. In this video, my friends, we're going to talk about the area of a region between two curves. So let's say you have a graph that looks like this. Let's call this f of x, and we have another graph called g of x. Let's say this is the x-axis and this is the y-axis. We want to find out the area between a region between two curves. Let's say f of x and g of x. So let's say I want to go from here. Let's say this is A and this is B. So I want to know the area between the area in between this here. By looking at this picture, we have a graph that is, the two graphs are above the x-axis. But what I'm going to show you is that the following technique of finding this area does not depend on whether it's on the x-axis, above the x-axis, or below the x-axis. All you need to know is that you need to be able to determine A and B, the endpoints where you want to compute the area. What you do need to be aware is that to find the technique for when you're gonna talk about integrals and sums, is that for when you're gonna, okay, let me set it up. Okay, so it says that the area between A and B is equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of x minus g of x, and then we multiply it by a term called delta x. And this, so basically one way to find this area, what this is saying is that we can take a rectangle and we specify delta x, and we can sum, we can do more, and we can approach, and this delta x can approach actually 0 as delta x approaches one second. As delta x approaches infinity, I'm sorry, as n approaches infinity, and delta x, I'm gonna put it here, delta x approaches 0. So you can make this approximation as closely as best as we want, as much as better as we want, by letting delta x approach 0. When you let delta x approach 0, then you get the area of the region. But for approximation, you can divide this. So basically, delta x is like a partition. It's called a partition. You let it you let the width of this rectangle as approach 0 or as small as you want, and then the height of this rectangle is gonna be f of x minus g of x. And what's the area of a rectangle? For any rectangle is the width times height. So we let delta x multiplied by f of x g of x. The only requirement for this here is that f of x has to be greater the g of x for this to work. And that's what we see on the picture. F of x is above g of x. But it doesn't matter whether this is here or here, as long as we know the endpoints, the range where we want to compute the area of the region. There is a special case that I'm going to talk after this one that makes we need a little trick, but the same idea and the same formula are used. So basically, by dividing this region into small rectangles, I compute the area by summing all these rectangles, and by letting delta x approach 0 and going and letting n approach infinity. In other words, we can divide this infinitesimally to get an exact area value. So you're gonna learn that this here, this formula here is the same thing. So instead of working with sums, we can work with integrals, and we can let this sum equal to, okay, now we specify endpoint for a to b, and then we take this here, f of x minus g of x of bx. Notice here we're integrating with respect to delta x, with dx, with respect to x. But the reason we do it is because this thing here, it's above, f of x is above gx. So we're computing vertical rectangles. So this formula is for vertical rectangles. Sometimes it would be better to compute a horizontal rectangle. Let me give you one example for that. Let's say your function, so you have your x and your y-axis, and then you have a curve that goes like this, and let's say we call this one g of x, and then you have another curve that goes like that, and let's call this one f of x. So in the previous graph, we were computing the integral from a function that from top to bottom. When we compute horizontal, so let's say we're gonna compute from here. This is your A and this is your B, and we'll compute horizontal rectangle. So we call this one delta y, and your partition is delta y. So now we're looking now to compute the integral or the sum. We're gonna subtract from right to left. So we're gonna do f of x minus g of x. So okay, so now the area, again, we let delta y approach 0. So that means we want to make it as small as possible. Make this thinner and thinner to get a better approximation. To get xi, you let the limit approach 0. Okay, so now the area in this case is going to be lim as n approaches infinity of the sum from I1 to n of f of x minus g of x times delta y. And that's gonna be equal to, again, we need to know the endpoints. It's gonna be a to b from f of x and actually let's call this one f of y because we're working with delta y. So let's call this one delta y. Okay, so now f of y minus g of y delta y. And of course, this is your I and your I. Okay, so now we take the integral with respect to y. So same concept, and actually you learned that what you can do with taking the integral with respect to x and with respect to y, it should give you the same answer. But sometimes it's better to use this one. It's easier. It's more intuitively easy. Okay. So now I'm gonna come back to the special example. A special example that you're gonna have to do similar same integral idea but using a different method. So let's say you have your x and your y, and then your graph looks like this. Okay, let's make this one a little. And then you're asked, and then you have another graph, another function that looks like this, and you're asked to compute from A to B So what's different about this graph? So let's let this one go g of x and this one called f of x. notice f of x is above, so between. So let's say you have a point here let's call this C. So from A to C, from A to C, f of x is greater than g of x, and from C to B, g of x is greater than f of x. And for all these problems, we know that the another thing that you need to be aware of is from A to B, in order to take the integral, then, or the sum from A to B, for all these techniques, f of x and g of x are continuous. On AB, the whole interval that you're working with. Otherwise, you can't do this. So the way you do it in this case, because we have to here, your graphs, the increasing and decreasing changes, we need to split the integral. So instead of doing A to B, what you need to do is that the area is equal to the integral from A to C of, and remember, we're going from top to bottom. We're gonna do it with respect to x. So let's see, A to C. So in this case, it's gonna be f of x minus g of x delta x, and then we add the integral from C to B of, now the top is gonna be g, so we switch g of x minus f of x delta x. So that's the only difference about this kind of problem. You need to split the interval into two parts or multiple parts if you get different graphs, if you get a different, depending on how the graphs look like. So we have looked at, so in all these things, we're talking about area of a region. So means here we're looking at this and this here. So we split it up. We split up this here and this here. You only do this when you switch increasing or decreasing of the functions. So on another video, I'm going to look at specific examples of computing area of a region. But in this video, I just want to teach you the theory and where these things come from. Thank you very much. Don't forget to subscribe, please.